Good morning, friends. I welcome you all for the another session. Okay, so today we're going to study stress block parameters. Okay, so this is one of the important term we're going to use before the analysis of beams. So in the previous case, we have seen that the different values like total compressive force, total tensile force in the stress block. So the same diagram we're going to draw. This is the cross section of the beam. Okay, this is the strain diagram. Okay, strain diagram. So see, it is in the form of triangle. So this portion, what we are seeing, this is for the concrete, and for steel it is just a line. Okay, and you can see here 0.0035. What is this 0.0035? This is the maximum strain in concrete here at the extreme fiber. Okay, here it is 0. See, here it is 0. Then it will goes on increasing. Somewhere here 0.002, and at the extreme fiber, compression fiber, the strain in concrete is 0.0035. Okay, so this is a strain diagram. Then we're going to mark this distance where the strain is 0.002. We're going to mark this as x1 and this as x2. So if you consider this total depth is xu. Okay, from here to the neutral axis, we already know that this is xu. So out of xu, this is x1 and this is x2. Okay, similarly you can see the stress diagram. Okay, so the stress diagram for this concrete, we are drawing only this concrete. So for this concrete portion, the stress diagram will be like parabolic. So this is the parabolic stress diagram for this concrete. Okay, and what is the maximum stress in the concrete? This is a stress, this is strain. Maximum strain is 0.0035. Maximum stress in the concrete at the extreme fiber is 0.45 FCK. Okay, 0.45 FCK. And this depth is up to the neutral axis. From top to this neutral axis is XU. Okay, and we already shown that. So in this compression zone, there will be a total force, total compressive force, capital C. We are writing this capital C is equal to, already we know that, stress into area 0.36 FCK into B into XU. Already we know that. Okay, so we're going to show in this section, that is 0.42 XU. What is this 0.42 XU distance? So this is the distance where the total compressive force C in the concrete, okay, total compressive force C in the concrete is acting, that is at a distance of 0.42, at a distance of 0.42 times of XU. If it is XU, okay, then where the C will be acting, total compressive force in the concrete, the C will be acting at a distance of 0.42 times of XU from top fiber. From this is 0.42 XU. This we are going to prove now. This is the important derivation. I mark this as important. So this will be asked in the examination. Okay, show that the total compressive force will be acting at a distance of 0.42 times of XU from the top compression fiber. This we are going to prove. Okay, for this what we need to do is draw the cross section of the beam, draw the strain diagram, and draw the stress diagram. Okay, show all these values, maximum compressive strain in concrete, then somewhere here we don't know, it will be 0.002. Okay, then mark this as x1, x2. So x1 plus x2 will be xu, total neutral axis depth. Okay, then this is stress diagram. Maximum stress in the concrete is 0.45 FCK. Okay, then we're going to show this total compressive force which will be acting at a distance of 0.42 XU. This only we have to show, prove. So then what is this diagram? Okay, this diagram is called as stress block. Okay, this diagram is called as stress block, or you can say that this complete diagram, strain and this Okay, so how are we going to define stress block? What do you mean by stress block? The diagram showing the distribution of compressive stress in concrete across the depth xu of the section is known as stress block. So what this diagram indicates? The diagram indicates distribution of the compressive stress. Okay, so here it is 0.45 FCK. So somewhere here it will be going to change. So at this point it is a total compressive force like that. So across the depth of the beam section, whatever the stress distribution is there in the concrete, that will going to show in the form of stress block. So the diagram showing the distribution of compressive stress in concrete across the depth xu. Across this depth xu, whatever the distribution of their compressive stress is known as stress block. Okay, and it is in the form of, see this diagram, the diagram is in the form of parabolic shape. It is stress diagram in the concrete is parabolic shape. Okay, now let us write down these terms. What are these terms? X1, x2 and other things. Let x1 is equal to, see this x1. Now see, can you see this stress diagram? Stress diagram, it is no doubt it is a parabolic shape. So again this parabolic shape can be divided into two parts. One is, see this rectangle part. Can you see this rectangle part? Okay, this is a rectangle part. So the height of this rectangle part will be x1. Height of the rectangle part will be x1, and this part, this is x2, and this is in the parabolic shape. So total this stress diagram can be divided into one, that is rectangle, and this will be parabolic. Okay, so that will going to give the shape of this stress diagram. Now again the height of this rectangle part we will going to consider as x1, then height of this parabolic part will be considered as x2. So x1 plus x2 will be x2. So this will be x1. Okay, not don't think that this C will be acting exactly center of this here. Okay, it is not xu. So it is again inside this will be less than this x1. Okay, so let us x1. What is this x1 or what is this x1? X1 is equal to height of the rectangular part of the stress block, this height of the rectangular part. Then x2 will be height of this parabolic part of the stress block. Now consider this strain diagram. Now x1, this is x2, and this is somewhere here it is 0.002 and maximum strain is 0.0035. So from this strain diagram I can write it as x2, this x2 divided by total height. So x2 divided by total height will be xu. So x2 divided by xu, that is equal to 0.002 divided by 0.0035. So only if you consider from similar triangles, there are two triangles now, this and this total triangle. So xu divided by total depth xu, x2 divided by xu, that is equal to 0.002 divided by 0.0035. So x2 upon xu is equal to, this term comes out as 4 by 7. Okay, this will be 4 by 7. So x2 by xu is equal to 4 by 7. Therefore x2 is equal to 4 by 7 into xu. So what is this xu? x2. So x2 is nothing but height of this parabolic part, this height from here to here, height of the parabolic part x2 is equal to 4 by 7 times of this xu. Okay, so similarly now I can find out x1. So what is x1 now? What is total? Total is xu minus x2. xu minus x2 will give height of rectangle part, height of this rectangle part x1. So x1 is equal to xu minus x2. So xu minus x2 is 4 by 7 xu. So therefore x1 we can get it as 3 by 7 xu. So first what we have to do, from the strain diagram, okay, we can find out x1 and we can find out x2. So x2 is, this x2 is 4 by 7 xu, and this x1 is, okay, 3 by 7 xu. First we'll calculate x1 x2, then we'll calculate this area. So the total area of this stress block is in the shape of parabolic. Okay. Now see, first we'll find out area of the parabolic part of this stress block. So this complete stress block, can you see parabolic? So again, it can be divided into this rectangle, okay, rectangle, and this parabolic part, this part. So height of rectangle is x1, height of this parabolic part is x2, and x1 and x2 values are these two. Okay. Now we can find area of the stress block. We know that area of parabolic section, okay, that is total area will be 2/3 of base into height. So since it is a parabolic shape, area of parabolic part is, this area of parabolic section is 2/3 of base into height. It is not triangle, it is parabolic, means 2/3 of base into height. But again this total area can be divided into a rectangle and this small parabola. So first we'll find the area of this parabolic part, this part. Can you see this part, this parabolic part, and this is rectangle part. First we'll find this area of this parabolic part. So I can write it as A2. Okay, area of parabolic part A2. So if it is a parabola, then the area will be 2/3 of base into height. 2/3 of base into height. So 2/3 base into height. Now see, what is the area of this part? So this will be 2/3 of base into height. What is the base now? What is this base? Base will be 0.45 FCK. And what is this height? This is x2. So area of this will be 2/3 of this base into this height. So that is 0.45 FCK is the base, and what is the height of this parabolic part? That is x2. Okay, this is x2, this is base. So 2/3 of this base into this height x2. So 2/3 of 0.45 FCK is the base, x2 will be the height. So substitute x2 value here. Okay, then we're going to get A2 is equal to 0.17 FCK XU. Okay, area of this part, parabolic part, area of this parabolic part. So area of parabolic part A2 is equal to 0.17 FCK XU. Now similarly, area of this rectangle part, now we're going to consider area of this rectangle part. So what is the area of rectangle? It is length into breadth. So this is the base, okay, and this is height. So if you multiply this base and height, what is the height? Height will be x1. This rectangle height will be x1 and base will be 0.45 FCK. So area of rectangle part is equal to B into L, that is 0.45 FCK is the base, and what is the height of the rectangle? It is x1. So substitute the value of x1, that is 3 by 7 XU. So we're going to get area of rectangle part, that is A1 0.19 FCK XU. Okay, so we have got area of parabolic part, and now we have got area of rectangle stress block part, that is 0.19 FCK XU. So A2 and A1 we have calculated. Now if you consider the total this stress diagram, okay, stress block, okay, so somewhere here centroid will be there. Okay, again for this to find out the total centroid of this parabola, again we are going to consider rectangle, then this parabolic part. Now see, now depth of the centroid of stress block, depth of centroid of this total stress block from the extreme fiber of the compression zone is y bar. If you consider this, where this C will be acting now, C will be acting, this is y bar. What we have shown here 0.42 XU is the y bar, that only we have to find out. So from extreme top fiber, this C will be acting at centroid Y bar. So Y bar we're going to find out now. Y bar is equal to, so how we'll find the centroid? Now again there are two areas now, A1 and A2. So A1 is area of rectangle, A2 is the area of this parabolic. Now see, this is a rectangle. Now there are two areas, this A1 and this A2. So this centroid will be, again there will be two centroid if you consider this rectangle and parabolic part. So what is the centroid of the rectangle? It is half of x1, only if you this rectangle. So centroid from this top will be half of this x1. Then centroid of this parabolic part will be this from the top again x1 plus this centroid of this, only this parabolic is 3 by 8 of this x2. Okay, now see, we have written here, so therefore this is y bar now. Okay, from top to where the C will be acting, that is y bar. So y bar is equal to A1. So A1 is 0.19 FCK XU, A1 into Y1. Y1 means centroid of this rectangle. Centroid of this rectangle from the top. Okay, so what is this centroid of this only rectangle? So height of, what is the height of the rectangle? It is x1. So rectangle means it will be half of this x1. So 0.49 FCK into x1 will be the area, into y1 is half of this x1, that is half of this x1. So half of x1 is 3 by 7 xu, already we have calculated, plus A2. What is A2? Area of this parabolic part, only this part. So A2 0.17 FCK XU, 0.17 FCK XU into, what is Y2? Y2 again from this top fiber to center of this parabolic part, So Y2 will be this x1 plus from this it is centroid. So what is that here? 0.17 FCK XU is the A2 into Y2. So Y2 will be this x1 plus x1 means 3 by 7 XU plus this, from this to centroid of this parabola is 3 by 8. Okay, it will be 3 by 8 of x2. Okay, so from here to here will be how much? x1 plus from here to here is, from this to this is 3 by 8 of this x2. So x1, this is 3 by 7 x1 plus 3 by 8 of x2, this is x2. So divided by total area. What is the total area? Okay, total area of this parabolic part is this 0.36 FCK XU. If you add these two, okay, if you add these two, A1 plus A2, A1 plus A2 will be the total area of this parabolic part. So centroid can be found out A1 plus Y1, then plus A2 into Y2. That will give total. A into Y bar. Okay, total area into this Y bar. This is Y bar now. From C to this top fiber, A into Y bar is equal to A1 Y1 plus A2 Y2. So if you substitute all these values, we will going to get Y bar is equal to 0.42 XU. So in the beginning classes we have written directly, okay, we have written directly this C, total compressive force C will be acting at a distance of 0.42 XU. Now how we have got this 0.42 XU? From this today's session. So we have got Y bar is equal to 0.42 XU. So this indicates that total compressive force C will be acting at a distance of 0.42 times of XU from the top. Okay, so this total compressive force in this concrete, we are talking about the concrete. So total compressive force in this concrete, that is C, will be acting at a distance of 0.42 times of this xu. So that is the derivation we have shown. So this is the important derivation. Okay. So I request once again you go through this derivation and try to solve once again this derivation, because this is an important derivation you may get in the examination. Okay, so I hope you understood this. Okay, if any doubt, please feel free to ask. Okay, once if you go through this, then afterwards I'll going to start with the analysis now. So if you understood all these previous classes, then it is easy to go for the next session, that is analysis of beams. Okay, so first we'll go start the analysis, we'll going to solve some problems, then we'll start with the design. Okay, so I hope you understood this stress block parameters definition, then how to prove that total compressive force C will be acting at a distance of 0.42 times of xu from the top fiber. So thank you very much for attending this session, and we'll meet again in the next session. Thank you.